In this video, we're going to talk about binary search. Here, we're starting to get into more complicated algorithms than we've talked about in the past couple of weeks. And this is where we start to take the things that we've learned in previous classes and sort of expand on them and adapt them and modify them. So in the past, we've always usually pretty much used linear search. So linear search, if you remember, starts at one end of the array, right? We usually use a single for loop with, say, an index I, and we move that index to the other end one step at a time until either you find the element that you're searching for or you reach the other end, which means that the element wasn't found, right? You got all the way across the array, right? So we have some array, and let's say we initially start here and we move all the way across. If we get to the end, then we didn't find it, right? Otherwise, maybe we found it here. And that works with any array of comparable elements, whether they're strings or ints or doubles or whatever. It doesn't matter, we don't know anything about the array itself. We just know that there's an array of elements that we can compare, and we're looking for something in particular. But what if we took that a step further? What if we did know something about the array? In particular, what if we knew that the elements in that array were in order, right? Meaning, what if we knew that that array was sorted? Could we do anything better than just making a scan from one end to the other? And that's where we get to binary search. So binary search only works for sorted arrays, right? The elements in the array have to be in order somehow. And instead of starting at one end or the other, we're going to start at the middle, right? So we're still going to have this index guy, and we're going to start at the middle. And it's going to say, if the search element is the middle one, then we return true, right? Yay, we found it. If the search element is not, then we're going to move the pointer and this range either to the middle of the left side of the range, if the middle is larger, because remember, we know they're in order. So if the middle point is bigger than what we're looking for, then we know what we're looking for has to be on the left side. Right? If the middle point is smaller, then we know if it exists, it has to be on the right side. And then we're going to repeat this process, making the range smaller and smaller and smaller until there's nothing left to search or we find the element we're looking for. So right away, it's quite obvious that this method sort of already leads itself to being recursive, right? We're already talking about ranges and passing it to the same method, right? But with different inputs, slightly smaller range of the input. So let's sort of work through an example. So you should have already read about this in the book, but here's an example just to go through as well. So here's our array, and as you can see, it is sorted, right? All of the elements are in order. And we're looking for, we're looking for this value 12, right? So what binary search is going to do is the whole range is everything here in green. And what binary search is going to do is it's going to start at 8, and it's going to say, well, 8 is not 12, right? And 8 is smaller than 12, which means if 12 is in the array, right, since it's sorted, we know that 12 can't be here, right? So let's look just at this side of the array and do the same thing. So we know it's not this guy, and we know it can't be over here. So it must be one of these three elements. So that's what binary search does. It goes over here and it says, okay, now this is our range, right? Just this. So I'm going to do the same thing. I'm going to say, here's the middle point. The middle point's 15. Well, 15 is larger than 12, which means, so it's not 15. And that means that it can't be on the right side here, which means it needs to be on the left side of the range. So it does it again. And now the range is just 12, but it turns out 12 is the number we're looking for, so it returns true. Right? So every time we're making that range smaller and smaller and smaller, looking for the element in question, using the fact that the numbers are sorted to help us reduce the search space. So let's try one more time, this time with the number 6. Notice that 6 isn't in the array. So let's see what happens when binary search tries to look for 6. So again, we start here, and it compares 8, and it says, well, 8 is bigger, so 8 is not equal, and 8's bigger, so it can't be on this side. Right? So we're going to search just this range here, and it searches the range, and it looks at 3, and it says, well, 3 is not equal to 6, and it's bigger, or it's smaller than 6, so that means 6 can't be over there. So then it reduces the range again, looks at 7. Well, 7 is not equal to 6, and it's smaller, so the range is now that. But that range is empty. There's nothing in it, which means 6 is not in our array. Right? So at each step, it first checks to see if the middle of the range is equal to our number. If not, it reduces the range down to the left or the right half and keeps going until the range is empty. So let's see what that looks like as code. So here is our binary search method, right? So remember that from the last group of slides, before, when we were using linear search, all we needed was the array itself and the find value and one of these two integers, right? Because we were just searching from one end to the other. But now we need these two because we need to define a range within the array. So what does binary search say to do? Well, it says first find the middle and check and see if that's how it compares with the thing we're looking for. Well, the first thing to do to find the middle is take the start and the range size. So the range size is n minus start. Add that to the start value. Because remember, so if you look at an actual array, right, and you look at some range within it, if this is I and this is j, the distance between I and j is j minus I. And then that first position is I, right? So now we're doing start plus the distance minus 2. That gives us the midpoint. And we need to compare it to find. So how are we going to compare it to find? Well, we're going to use an if statement. So if the thing we're looking for is equal to the midpoint, then we're going to return true. If it's not equal, then we need to do something, right? But now we're not just doing something, right? We don't need just an else. We actually need to break this down even further. So otherwise, if it's greater than that point, we're going to do one thing. If it's smaller than that point, we're going to do another, right? And what we're going to do is make a recursive call, right? We're going to recall binary search with a smaller range. Because remember, our find doesn't change, our array doesn't change. It's just the range that changes. So here, it shouldn't be find in array. It should be binary search. Again, the array stays the same, and the search value stays the same. And now, if our midpoint was bigger, right, that means our search value is smaller, which means it needs to be on the left side, which means the range starts at start and ends at mid minus 1. So remember, we have this array, and we have some range we're searching over. And we have start and end and mid, right? So we either need to search this guy or this guy. And remember, we never need to search mid because we've already checked its value. Right. So if mid was bigger, then we're going to check this first side, which goes from start to mid minus 1. And if it's smaller, oh, I have to redraw that picture. Right? If the midpoint was smaller, which means this is false, we know it's not equal to, so it's either larger or smaller, then it goes from midpoint plus 1 to the end. Right? And again, these should be so what's missing? Eventually we're going to keep doing this until we end up where there's only one element left, right? Or 0 elements left. Yeah, so we need our base case. So we're going to put that in here. If start is equal to end, then we're going to return whether that last element is equal to it. And there's actually a missing case here, right? So if end is greater than, or sorry, is less than start, right? So if we've done this math, right, because we're skipping 1 and a little bit every time, so we could end up that this range is negative, like we saw in the lab, right? If this range is negative, then we definitely didn't find the element because there's nothing left. But if it's just one element left, then we check it to see if it's the element that we're looking for. So sometimes when we look at recursion, we look at what's called a call tree or a stack, right? So this is sort of what the binary search tree looks like. Binary search call tree looks like. So we start with our initial call to the array we're looking for, the find element that we're looking for, and the range is initially 0 to n minus 1. Right? It's the whole array itself. And then say it's on the left side, right? We know that f is smaller than the midpoint. Then it makes this recursive call here, right? It could have made either this recursive call or that one. And here, maybe it's on this side, and we keep going. Eventually, we might get down to just a single element, right? Worst case scenario, we search the whole depth of this tree. And the nice thing is the depth of this tree is only log n, right? Which means at most we make log n calls to find an array. So we'll go into more depth on running times later, but if you think about the algorithm that we had for linear search, where we started at one end and we moved every element all the way down, right? Here we needed n steps if it wasn't in the array, whereas with binary search, we only need log n steps. So there'll be another video released in a couple days on running time analysis, but for now, just keep that in mind, that binary search is faster in the worst case than linear search.